Welcome to the explanation video of Know Thyself, Transferable Visuomotor Control through Robot Awareness. We define robot-aware control as robotic controllers that can distinguish between the robot and world and leverage this awareness to improve its capabilities. In this paper, we propose robot-aware dynamics models and planning costs in the visual foresight framework and demonstrate how a visual motor controller trained on a low-cost Widow X arm can be zero-shot transferred onto a very different robot, such as the Franka Panda. First, I'll give a brief overview of the robot-aware control framework. The first step is to train a robot-agnostic world model from videos of one robot. We collect videos of the training time robot doing random interactions in the environment. Next, we train the dynamics model composed of a robot and world module. The robot module is analytical since we know exactly how to compute the dynamics of the robot. The world module is conditioned on the analytical robot module. After training, we would like to transfer the model to a new robot and do prediction and control. The controller is given the goal image and start image. The robot-aware cost function enables the use of goal images without robots or even humans. To transfer the model to a new robot, we first reuse the world model. Next, since we have access at test time to the new robot's analytical model, we can simply plug that into the world model. Now we can use both model and cost function to do model predictive control. Let's take a closer look at the robot-aware dynamics model architecture. First, we feed in the image with the robot masked out, the action, and the robot state to the world model. Note that we feed in the robot mask as a spatial representation of the robot state to the world model. Because we have access to the robot dynamics model, we can also compute the future robot state and feed that into the world model as well. The world model then outputs the future image. We train the world model with the world loss, which only measures the error over the world region. To generate accurate robot masks for training and evaluation, we use camera calibration, the robot's 3D model, and a renderer to project the robot's 3D model into a 2D binary segmentation map. Here, the computed masks are visualized as the black overlay on the right-hand side. We highlight our zero-shot Widow X200 robot to Franka Panda robot control experiment. In this experiment, we trained the dynamics model on about 2,000 videos of the Widow X200 and then utilized the dynamics model for control of an unseen Franka Panda robot. Here, the baseline method chooses to move the robot out of the scene to minimize the pixel-wise cost, or outputs actions that exploit model error. As a result, it fails on all of the pushing tasks. On the other hand, our robot-aware dynamics model is able to accurately predict object movement despite the new robot, and the robot-aware cost correctly ignores the robot pixels in the image, resulting in much higher success of the overall controller. It appears to be too hard for the baseline dynamics model trained on one robot to generalize to a completely new robot. Therefore, in order to improve robot generalization, we train the models on 4 different robots before transfer. While the baseline controller's performance increases from 0% to 36%, it still suffers from the problems of the single robot training setup and fails on the majority of pushing tasks. After training on multiple robots, the robot-aware controller's performance increases as well from 71% to 90%. Here, we visualize the top 5 action trajectories that minimize the cost for each method. The goal is to push the watermelon down. The baseline method transfers poorly to the new Franka robot. It seems to treat the Franka robot as the background and overlays the training time robot over the Franka and moves it in random directions. In contrast, our method outputs sensible trajectories. We present some more zero-shot Franka prediction visualizations. In this example, our robot-aware dynamics model more accurately predicts the new robot movement and its interaction with the octopus compared to the baseline. The baseline simply overlays the Widow X robot over the Franka robot, blurs the octopus, and predicts less motion compared to the robot-aware dynamics model. The baseline's trend of overlaying the training time robot and predicting smaller movements is a consistent pattern we noticed across all datasets when transferring to new robots. The baseline's object dynamics prediction, a crucial property of control, is also impacted. The objects are prone to disappearing over time. In the bottom left example, the baseline's shark disappears over time, while our model retains the size of the shark. In the few-shot transfer experiments, we trained the visual dynamics model on video data collected from 3 different robots in RoboNet and fine-tune the models on about 400 videos of the Widow X200. After fine-tuning, the baseline dynamics model can adapt to the new robot, but our model still has better object dynamics prediction. The control trends are similar to the zero-shot experiment, where the baseline attempts to move the robot out of the scene or exploits model error to optimize the cost. Finally, we evaluate the performance of the robot-aware cost function on goal images without robots or with humans in the scene. While the pixel cost is sensitive to the size and appearance of the robot in the image, the robot-aware cost is invariant to the robot in the image. First, we take a goal picture with a human. By acquiring a mask of the human, either through annotation or human pose estimation algorithms, we can then plan with the robot-aware cost that ignores the human hand region. Similarly, we can use goal pictures with no robot in the scene. Our experiments show that the robot-aware cost can handle presence of distractor agents like human or absence of the current robot, while the pixel cost fails. In conclusion, we integrate robot awareness into visual dynamics models and planning costs to enable transfer across very different robots.